one of today's most prominent and advanced physicists has expressed his opinion on the matter. Michio Kaku, recognized for his outstanding contributions to the fields of physics, has recently confirmed that the James Webb Space Telescope has discovered 6 massive galaxies that scientists thought could not exist. These investigations have the potential to open up new dimensions in our scientific understanding of the universe. The discovery is both exciting and revolutionary, challenging existing theories about the formation and development of galaxies. It is, therefore, worth keeping an eye on these developments. The confirmation by such a distinguished scientist as Michio Kaku underscores the importance of these findings. Michio Kaku is an outstanding figure in the scientific field, a physicist of American and Japanese heritage, who is regarded as an expert in both classical experimental physics and quantum mechanics. Unlike some more conservative and skeptical scientists, Kaku does not belong to that group and has been receptive to the amazing results of the James Webb Space Telescope mission. His willingness to embrace new discoveries and share them with the public highlights his commitment to advancing our understanding of the universe. We are delighted that this distinguished scientist has decided to break his silence and publicly share what can no longer be denied. His enthusiasm and an almost amused tone are evident in his comments on the discovery made by the James Webb Space Telescope, a discovery that has piqued his interest. Join us as we explore the implications of Michio Kaku's discovery of these 6 massive galaxies. Kaku is a scientist who has always been willing to consider new theories. Throughout his life, he has demonstrated an openness to ideas that challenge the status quo, understanding that Einstein's, Newton's, and the relativity equations, while foundational, are insufficient to capture the full complexity of the universe. Kaku understands that the discovery of these new galaxies has the potential to enrich the scientific field. However, many of his colleagues have not been able to adopt this view, and it is generating concern and even insomnia among proponents of the Big Bang Theory and opponents of quantum mechanics. This, however, only provokes laughter from Kaku. The James Webb Space Telescope has shown the discovery of 6 massive galaxies dating back to the very beginning of the universe. Each of these galaxies contains more stars than our own Milky Way, despite having formed only 200 to 700 million years after the Big Bang occurred. The group of astronomers who made the discovery have dubbed these exceptional galaxies as universe breakers because, if confirmed, they would revolutionize our entire understanding of the universe. The implications of these findings are profound, suggesting that the universe's early years were far more dynamic and complex than previously thought. Something doesn't fit here anymore. The Big Bang Theory tells us that the cosmos was a hot mess after the initial event. The first solid objects took hundreds of thousands of years to form, and it took hundreds of millions more years for these objects to reach sufficient density and produce light. The formation of complex structures such as galaxies was assumed to occur much later. Some of the newly discovered galaxies exceed the Milky Way in size, and their immense luminosity indicates that they were probably forming hundreds of new stars each year, whereas our galaxy forms stars only sporadically. It remains uncertain exactly when the first galaxies formed. Researchers have not been able to determine this so far. The only thing that is clear is that initially, there may have only been single stars or groups of stars, which eventually joined together to form ever-expanding structures, leading to the development of dwarf galaxies. The small galaxies encountered other galaxies and gradually grew. According to previous theories, highly organized and massive galaxies could not have existed at that time, which raises the question, is the universe much older than previously believed, or did complex galactic arrangements develop much earlier? This circumstance is difficult for conservative science to accept, as it still finds problems with this model. Some branches of physics heavily refuse to accept this discovery and question possible errors in the age calculations. Kaku is aware of this and had this to say. There are many examples of old and false theories that stubbornly continue because of the prestige of some scientists. Many of these theories were only discredited when a crucial experiment revealed their falsity. Therefore, the fundamental work in any science, especially in physics, rests within the experimentalists who keep the theorists honest. In fact, on Earth, we know very little about the true beginnings of the cosmos. This quote from Kaku emphasizes the importance of continuous experimentation and validation in the scientific process. The Big Bang Theory was established in 1927 based on observations of the expansion of the universe. These data led to the conclusion that the cosmos originated from a single point and has been expanding ever since. At the time, it was difficult for people and scientists to conceive of a universe with a beginning and an end. The idea of a universe that had always existed and was infinite in time and space was beyond people's imagination. Even today, scientists still face difficulties in understanding it. However, it is important to reconsider these probabilities. Once again, these new demonstrations do not fit at all with what researchers have based for decades on the Big Bang theory. However, scientific evidence has shown time and time again that re-evaluation and openness to new ideas are a crucial component of the scientific process, just as is the confirmation of certain theories and observations. When Einstein was a child, it was believed that the stars and planets were firmly fixed in the universe, occupying defined spaces. However, we now know that everything in the universe is moving. Planets orbit stars. Stars move within their galaxies at hundreds of kilometers per second. Entire galaxies move swiftly across the universe, the fate of which we cannot yet even predict. This dynamic understanding of the universe challenges long-held beliefs and underscores the need for ongoing inquiry and adaptation in scientific thought. Today, scientists are challenged to accept uncomfortable truths and understand that theories are not absolute truths until they are rigorously tested or confirmed by accurate observation. The idea of the Big Bang arose from the realization that galaxies are moving away from each other, and this distance is proportional to their distance from Earth. This observation, known as Hubble's law, suggested that the universe was expanding. For a long time, elements such as cosmic background radiation and the redshift of light from distant galaxies seemed to support this theory. However, it is important to remember that, in the past, people who believed that the Earth was flat and that the Sun revolved around us also had physical evidence for their assumptions, until technological improvements provided a clearer and more accurate picture. Right now, we are witnessing a similar situation. Scientists expected the new James Webb Space Telescope to confirm assumptions related to the Big Bang, but instead, they have come across 6 galaxies that seemed impossible. This principle applies to light as well. When a celestial object moves away from us, its light shifts toward the red end of the spectrum, a phenomenon known as redshift. Conversely, if an object moves toward us, its light shifts toward the blue end of the spectrum, known as blueshift. Astronomers use this concept to measure the velocity and distance of galaxies. The greater the redshift, the farther away and older the galaxy is. The James Webb Space Telescope has detected galaxies with an extreme redshift, indicating that they formed just a few hundred million years after the Big Bang. However, their sheer mass and complexity contradict what scientists expected from galaxies at such an early stage of the universe. The shockwave in cosmology. The discovery of these 6 massive galaxies has sent shockwaves through the scientific community. If the observations hold, it would mean that galaxies formed and evolved much faster than previously thought. This raises profound questions. Did galaxies start forming earlier than we assumed? Are we missing key physics about how galaxies grow and evolve? Could our estimates of the universe's age and expansion rate be incorrect? These questions have led some scientists to propose modifications to existing theories, while others are more cautious, suggesting that additional verification is needed before drawing conclusions. Michio Kaku, however, finds the discovery thrilling. Unlike many who resist paradigm shifts, he embraces the possibility that our current models of the universe may need serious revision. He argues that science must remain open to change, as history has shown that new discoveries often challenge long-standing beliefs. The role of the James Webb Space Telescope. The James Webb Space Telescope, JWST, was designed to look deeper into space and further back in time than any previous observatory. Unlike the Hubble Space Telescope, which primarily observes invisible and ultraviolet light, JWST operates in the infrared spectrum, allowing it to peer through cosmic dust and see some of the earliest galaxies ever formed. JWST's first images revealed structures that many astronomers did not expect to see. These galaxies are not only massive but also well-formed, suggesting that star formation and galaxy evolution may have occurred at a much more accelerated rate than predicted by the Big Bang model. A turning point in cosmology? If confirmed, these discoveries could force a major revision of modern cosmology. Some researchers speculate that an unknown force or process may have accelerated galaxy formation in the early universe. Others wonder if the universe is older than we currently estimate, a controversial idea that challenges decades of scientific consensus. For Michio Kaku, these findings reinforce the idea that science is always evolving. He reminds us that many once accepted theories, such as the steady-state theory, which proposed that the universe had no beginning, were eventually discarded in favor of better models. The Big Bang theory itself was met with skepticism when first introduced, and now it, too, faces challenges from unexpected discoveries. Kaku emphasizes that no theory is sacred. Instead, he believes that scientific progress depends on constant questioning, experimentation, and adaptation. The beauty of science, he says, is that it's not about dogma, it's about discovery. We must follow the evidence, wherever it may lead. What comes next? The scientific community is now eagerly awaiting further analysis of these galaxies. Astronomers will conduct spectroscopic studies to confirm their distances and determine whether alternative explanations exist for their unexpected size and brightness. Some researchers speculate that new physics, perhaps related to dark matter, dark energy, or unknown forces, might explain these anomalies. Others argue that modifications to the Big Bang model may be necessary to incorporate these findings. Whatever the outcome, one thing is certain: the James Webb Space Telescope has already begun rewriting our understanding of the cosmos. As Michio Kaku and other forward-thinking scientists suggest, this is just the beginning. If the universe is full of surprises, then science must remain open-minded, adaptable, and fearless in the face of the unknown. Final thoughts. The discovery of these 6 massive galaxies challenges our most fundamental assumptions about the early universe. Whether this leads to a refinement of the Big Bang theory, the birth of a new cosmological model, or an even greater cosmic mystery, one thing is clear: we are witnessing a scientific revolution in real time. Michio Kaku's excitement is well-founded. The James Webb Space Telescope is not just confirming what we already knew, it is forcing us to reconsider everything we thought we understood. And that, perhaps, is the most exciting discovery of all. Because the sound of the engine varies as the car moves, the same is true of light. When a light source, like a distant star, moves toward us, the light we perceive shifts toward blue hues. On the other hand, when the light source moves away from us, the light shifts toward redder hues. This phenomenon is called redshift. Redshift has been transformed by physicists into values representing velocities and distances for measurement in the study of the cosmos. However, it is important to note that these measurements, even if off by a few millimeters, can have significant effects. The measurement methods that were previously employed are currently under review, and it is interesting to see what results scientists will arrive at regarding the most recent demonstrations related to our cosmos. It is necessary to consider whether these findings are really based on redshift errors or whether some scientists are simply denying the facts. This is a question that requires rigorous analysis and careful review of the data and methodologies used in the research. The current scrutiny and re-evaluation of measurement techniques highlight the evolving nature of scientific investigation. Many thanks for watching the video. As always, we remind you that you can post your doubts in the comments box. If you liked Michio Kaku's analysis video, do not forget to hit the like button, share it so it reaches more people, and subscribe to the channel so you don't miss more content like this. Thank you so much for watching. This call to action encourages viewers to interact with the content, helping to build a community of curious minds eager to explore and understand the most recent discoveries in science. The study of our universe, with its vast expanses and intricate celestial bodies, continues to captivate and challenge scientists across the globe. From the early theories of the cosmos to the latest discoveries made possible by cutting-edge technology, each revelation changes how we perceive the universe and pushes the boundaries of human knowledge. One of the most profound and enduring questions in cosmology revolves around the origin and evolution of galaxies. Galaxies are cosmic cities of stars, gas, dust, and dark matter, bound together by gravity. Understanding how galaxies form and evolve is crucial not only for unraveling the mysteries of our universe but also for confirming or challenging existing theories such as the Big Bang theory. The Big Bang theory, proposed nearly a century ago, posits that the universe originated from a singular, infinitely dense point and has been expanding ever since. This idea emerged from observations of the universe's expansion and the cosmic microwave background radiation, which is considered the remnant of the early universe's intense heat and light. However, recent discoveries, particularly those made by the James Webb Space Telescope, JWST, have challenged some fundamental assumptions underlying the Big Bang theory. The JWST, with its unprecedented sensitivity and resolution, has detected galaxies that defy conventional understanding. These galaxies, dating back to within a few 100 million years of the Big Bang, are unexpectedly massive and luminous, suggesting a more dynamic early universe than previously envisioned. The implications of these findings are profound. They raise questions about the timeline and mechanisms of galaxy formation, forcing scientists to reconsider existing models. For instance, the discovery of galaxies that are already so evolved shortly after the Big Bang challenges the notion that galaxy formation was a slow and gradual process occurring over billions of years. Moreover, JWST observations have highlighted the complexity of galactic evolution. It is now evident that galaxies can grow rapidly and host significant star-forming activities early in their histories. These insights compel astrophysicists to revise their theories on how gas, dark matter, and stars interacted in the infancy of the cosmos to form the first galaxies. Beyond revolutionizing our understanding of galaxies, these discoveries emphasize the critical role of technological advancements in pushing the frontiers of astrophysical research. The JWST, with its infrared capabilities, allows scientists to peer deeper into space and further back in time than ever before. By studying the light emitted by distant galaxies, astronomers can reconstruct their histories and uncover clues about the conditions that prevailed during the universe's formative years. The concept of redshift, a key tool in cosmological research, plays a pivotal role in these investigations. Redshift refers to the phenomenon where light from distant celestial objects shifts to increasingly long wavelengths as they move away from us. This effect, known as cosmological redshift, provides valuable information about an object's distance and velocity relative to Earth. Through meticulous data analysis, scientists use redshift to infer the size, age, and evolutionary stage of galaxies observed by telescopes. However, interpreting redshift measurements requires accurate calibration and a thorough understanding of potential error sources, such as gravitational lensing and instrumental limitations. In addition to studying individual galaxies, astronomers are also exploring larger cosmic structures, such as galaxy clusters and superclusters. These vast assemblies of galaxies are bound together by gravity and offer insights into the distribution of matter on cosmic scales. By mapping the spatial arrangement of galaxies and measuring their velocities, researchers can trace the cosmic web, a filament-like structure that spans across the universe and defines the large-scale architecture of galaxies. The cosmic microwave background, CMB, radiation represents another invaluable source of information for cosmologists. Discovered accidentally in 1964, the CMB is the faint glow of radiation left over from the Big Bang itself. As the universe expanded and cooled, this early heat settled to a few degrees above absolute zero, leaving behind pervasive background radiation. Detailed measurements of the CMB's temperature fluctuations provide insights into the universe's infancy, revealing primordial density variations that eventually gave rise to the galaxies and cosmic structures we observe today. These primordial density variations, detected in the cosmic microwave background, CMB, serve as a blueprint for the large-scale structure of the universe. Tiny fluctuations in temperature and density influenced how matter clumped together under gravity, leading to the formation of the first galaxies, stars, and planets. The study of these fluctuations provides crucial insights into the fundamental properties of the universe, including its overall composition, rate of expansion, and even the nature of dark matter and dark energy. Dark matter and dark energy, the unseen forces shaping the cosmos. One of the greatest mysteries in modern cosmology is the nature of dark matter and dark energy. While ordinary matter, composed of atoms, makes up only about 5% of the universe, dark matter and dark energy dominate the remaining 95%. Dark matter, though invisible, reveals its presence through gravitational effects. It acts as an unseen scaffolding, holding galaxies together and influencing their rotation. Without dark matter, galaxies would not have enough mass to explain the speeds at which their outer stars orbit. Scientists have mapped dark matter's distribution by observing the way its gravity bends light from distant objects in a process called gravitational lensing. Despite extensive research, the exact nature of dark matter remains unknown, and various theories suggest it could be composed of exotic particles that interact only weakly with normal matter. Dark energy, on the other hand, is even more mysterious. It is the force driving the universe's accelerated expansion. In the late 1990s, astronomers studying distant supernovae discovered that the universe's expansion was not slowing down, as previously expected, but was instead speeding up. This surprising revelation led to the realization that some unknown energy, termed dark energy, was counteracting gravity on a cosmic scale. Current estimates suggest that dark energy constitutes roughly 68% of the total energy in the universe, yet its true nature remains one of the biggest unanswered questions in physics. The future of cosmology, new frontiers and discoveries. With advancements in observational technology, the next few decades promise to bring even greater breakthroughs in our understanding of the cosmos. The James Webb Space Telescope, JWST, has already reshaped our view of the early universe, but upcoming missions like the Nancy Grace Roman Space Telescope and the Euclid Space Telescope aim to provide even deeper insights into dark energy, dark matter, and galaxy evolution. Moreover, the study of exoplanets, planets orbiting other stars, continues to expand our understanding of planetary systems beyond our own. By analyzing the atmospheres of exoplanets using powerful telescopes, scientists hope to uncover signs of habitability and, possibly, extraterrestrial life. On an even grander scale, theoretical physics continues to explore ideas such as the multiverse theory, the nature of space-time, and the possibility of quantum gravity, a long-sought theory that would unify Einstein's general relativity with quantum mechanics. These investigations may one day provide a deeper understanding of the fundamental laws that govern our universe. Conclusion: a universe of endless discovery. As scientific knowledge advances, each new discovery leads to more questions, deepening our fascination with the cosmos. The study of redshift, dark matter, dark energy, and cosmic evolution is not just about understanding the universe's past, it is about uncovering the forces that shape its future. With cutting-edge technology and an ever-growing curiosity, humanity stands at the threshold of a new era of cosmic exploration. The journey to understand the universe is far from over. Each breakthrough challenges our perceptions and pushes the limits of what we know. Whether through telescopes peering into the distant past, satellites mapping cosmic structures, or physicists probing the very fabric of reality, one thing remains certain: the universe will continue to surprise and inspire us for generations to come.